Hi guys, this is Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland. And this short video is going to deal with, I suppose, how to apply the Affine Cipher. Okay, it's an algorithm that allows us to encrypt a piece of plain text, and also it's an algorithm that allows us to decrypt a piece of ciphertext. Okay. Now what I'm going to do first is this short video is going to just deal with the encryption phase, okay, of this algorithm. The next video will deal with the decryption phase. But what I'll do is, since it's the first video in this particular series on the Affine Cipher, what I'm going to do is I'm going to just pull out two formulas. The first formula represents the encryption phase, and the second formula represents the decryption phase. Well, maybe what I'll do is I'll just present them two formulas first of all. So the encryption, okay, so the encryption phase, or the encryption cycle, okay, the formula that we rely on is this. It's C is equal to A times P plus B modulo M. Okay, a lot of symbols here, and I haven't defined these symbols just yet. Okay, but maybe what I'll do is I'll just walk through them really quickly. Okay. So what we have is we have a piece of plain text. Okay, it's made up of characters, and what we do is we associate each character in the plain text with a number. Okay, where the number, for example, the number is a number that represents its position in our alphabet. Okay, and I'm going to do that in a little while. So P is a numerical representation of a character. Okay, then what we do is we choose two numbers, A and B. Okay, these two numbers that we choose have some constraints on them. Okay, the constraints are relative to this number m, where m is the size of our alphabet. The important thing is that when we choose the value a, that the value a is less than or equal to m, and also when we choose the value b, that that's also less than or equal to m. But one other condition associated with this particular cipher is that the value a, which on the first condition must be less than or equal to m, it must also be relatively prime to m. Okay, which basically means it should not share any non-trivial divisors with m. So in other words, the greatest common divisor between a and m should be equal to 1. Okay, so once you have all these numbers, okay, you have the number a, you have the number b, and you know your alphabet size. Well, what you do is you take a numerical character or character in your plain text, convert it into a number, you multiply that number by the value a, you add on b, and then you find the remainder after division by your alphabet size, m, and this will give you another number, which we're calling the ciphertext number. Okay, which when we look up on our alphabet, will give us a ciphertext character. That's the cipher character associated with the plain text character p. So that's the encryption cycle. The decryption cycle. Okay, the decryption cycle has a formula, and the formula looks something like this. It says that P is equal to A inverse times C minus B modulo M. Okay, so once again we've defined some of these characters. Okay, M is the size of our alphabet, B is the constant that we picked in phase 1. Okay, C is the ciphertext representation of the plain text that we encrypted in the encryption cycle. But I suppose more importantly, this A inverse is the multiplicative inverse of A. We say it's the multiplicative inverse of A in the group modulo m. Okay, that's a little bit complicated, but we'll come back to how we calculate this special value, this A inverse value, when we get to the decryption cycle. Okay? But what's important here is that once again we have 1, 2, 3, 4 numbers. 3 of them we know from the encryption phase. We know the size of the alphabet, we know the constant b, and we also know the ciphertext value, which is c. So the only thing to calculate is this inverse, this A inverse. And once we have that, we take the value b away from c, we multiply that by the A inverse, and then we calculate the remainder modulo the alphabet size m, and that gives us a value back, which is the plain text value, which should match the plain text value that we passed in through the encryption cycle. Okay. Sorry, that was very fast, I think, there. So maybe what I should do is let us just list off all of these characters and what they represent. Okay, so our symbols. So let's list these off. Our symbols. So what we'll do is we'll say P. Well, P is a plain text character. Okay, and I'll just write down as a number. Okay, so it's a numerical value associated with that plain text character. Okay, we have C is a ciphertext character. Okay, that's the encryption of P. Okay, but it's as a number. Okay, also, or as an integer. Okay, M is the alphabet size. Okay, how many characters are in our alphabet? Okay, B is simply a number that's greater than or equal to 1 and less than or equal to M. Okay, and A is also a number that's greater than or equal to 1 and less than or equal to M, but there's also another condition, is that the greatest common divisor between A and M must be equal to 1. Okay, and this is really, really important for this algorithm to work. The GCD of A and M must be equal to 1. Really what we're saying is that the only common divisors between A and M should be 1. Should be no other number. Okay, so they're all our symbols. So maybe what we'll do is we'll take a piece of plain text and we'll encrypt it. Okay, so let's consider the English alphabet. Now let's just make everything lowercase. Okay, so our characters are A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. Okay. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. And I think we knew that already, that there's 26 letters in the English alphabet. Okay? Well, 26 lowercase letters in the English alphabet. So in this case here, what we have is we have M is equal to 26. It's our alphabet size. Okay? Doesn't have to be this, it could be a larger alphabet, but for this purposes we'll choose M is equal to 26. Okay, brilliant. Now what we do is, for each character in our alphabet, we give it a numerical representation. And what we'll do is we'll say 1 is associated with 0, A is associated with 0, B with 1, C with 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and 25. So although we have 26 characters in our alphabet, we start counting from 0 through to 25, which still gives us 26 characters. What I'll do is I'll just put a line through this here so that we separate off these particular encodings. Okay. So this is our alphabet and each character's numerical representation. Okay. So in the encryption phase, it's important that we choose two numbers, A and B, and them numbers must be less than or equal to M. Okay, so we need to choose an A, we need to choose a B. Let's just say we choose B to be equal to 7. There's no other condition on B other than it has to be a number less than or equal to M. I could choose any B value that's less than or equal to M, less than or equal to 26, and greater than or equal to 1. In this case, let's just choose 7. Okay. And what I also want to choose is I want to choose a value for A. It's important that A is a number between 1 and 26. That's less than or equal to M. But more importantly, this number must be its greatest common divisor between itself and M. Itself and 26 must be equal to 1. And now I'm just going to pull a number out of the sky. The number I'm going to choose is the number 15. Okay. Actually, let's just consider the number 15. Okay, so considering 15, its divisors are, they're 1. 2 doesn't divide into 15. 3 does. 4 doesn't. 5 does. 6 doesn't. 7 doesn't. 8 doesn't. 9 doesn't. okay, and so on. 10 does not, 11 does not, 12 does not, and so on. 15 does. So what we end up with is the divisors of 15 are these numbers here. The divisors of 26, okay, the divisors, okay, are 1, 2, 4, 6, 12, okay, and 26. Okay. So what we can actually see is that the only commonality between the divisors of 15 and the divisors of 26, the only common divisor that we have is 1. Okay? And this is an important condition, okay? Because the greatest common divisor between A and M must be equal to 1. And that's why I picked 15, okay? As one example. We could have picked 7. We could have picked many different numbers between 1 and 26, but for this particular example, I'm choosing 15. Okay, so now that we know, okay, what our parameters are, okay, our parameters, okay, what we need to do now is we need to take a piece of plain text and we need to encrypt it. Okay, so let me give you a piece of plain text. The plain text is, I am a secret. Okay, so there it is there. So the first thing we need to do is we need to convert each character into its numerical representation. Okay, so we need to convert the characters. So convert to numbers. Okay, I goes to 8, so this is 8. A goes to 0. M goes to 12. A goes to 0. S goes to 18. E goes to 4. C goes to 2. Or goes to 17. E goes to 4. And finally we have T goes to 19. Okay? So what we need to do now is we need to take every single one of these numbers. Okay? Each one of these numbers is going to be a particular value of P, the plain text. Okay, so now we need to do our encryption. So our encryption, okay, the encryption phase or the encryption cycle. Okay, don't forget, M is 26, A is 15, B is 7. Okay, so when P is equal to 8, okay, so when we take I, which is represented as an 8, the encryption phase says, okay, the encryption phase says that we should multiply the P by our A, add on B, and calculate the answer modulo M. Okay, so what we should do is the encryption, our encryption algorithm, okay, says that the ciphertext is equal to our A value times our P value plus our B value modulo M. So in this situation here, the ciphertext is going to be equal to our A value. Now we know what our A is. We've chosen A to be 15. So it's going to be equal to 15, okay, times our plain text, which is 8, okay, plus our B value. We've chosen B to be 7, okay, and we need to calculate that modulo the size of our alphabet, which is 26. Okay, so let's do this and let's see what we get. Okay, so I'm just going to turn on my calculator here. Okay, mode 0. There we go. So let's do what's inside the brackets. 15 times 8 gives us a value of 120, plus 7 gives us a value of 127. So our C, our ciphertext, is 127 modulo 26. So the question now we're asking is, okay, after I divide 26 into 127, what's left over? Well, let's see, how many times does 26 go into 127? So 127 divided by 26, it goes in roughly 4 times. Okay, so what we know now is this, is that 127 is equal to 26 times 4 plus some remainder. Okay, well, 26 times 4 is 104, and 127 minus 104 gives us a value of 23. So the remainder here, so what we have is 127 must be equal to 26 times 4 plus 23. So our C value, C is equal to 23. Now, so really what we're saying is this, is that when we look up 23 on our encoding, 23 is associated with an X. So what we know is this, is that P, which was represented the I, okay, so the I is taken to C23 is taken to X, okay. And we continue in this fashion, encoding our characters. So when P is equal to 0, we get our ciphertext C must be equal to, well, it's equal to A, which is 15, times 0, plus B, which is 7, modulo 26. Well, this gives us C must be equal to 7 modulo 26. 26 into 7 goes 0 times with a remainder of 7, so C must be equal to 7. Or what we're saying is this, is that the letter A, which represents a 0, is encoded to the letter 7, and the letter 7 is a H. So what we have now is we have A, so we have C is equal to 7, or we have the letter A is taken to the letter H. And we continue in this fashion for all of our numbers, taking them and encoding them. The next number is 12, so when P is equal to 12, the ciphertext must be equal to A, which is 15, times P, which is 12, plus 7, modulo 26. So in this situation here, we have 15 times 12 gives us 180, plus 7 gives us 187. So C must be equal to 187 modulo 26. Now, how many times does 26 go into 187? So we have 187 divided by 26. It goes in approximately 7 times. So what I know is this, is that that 187, okay, must be equal to 26 times 7 plus some remainder. Okay, well, what's 26 times 7? Well, 26 times 7 is 182. What do I add on to 182 to give me 187? Okay, well, I add on a 5. So in this case, R is equal to 5. So we have 187 must be equal to 26 times 7 plus 5. Okay, our R is 5. Okay, so really what we're saying here, the remainder, that's what we're interested in. The remainder, we're always interested in the remainder. The remainder is 5, so C is equal to 5. In this situation, we're saying the letter M, which was encoded as a 12, is taken through to the encryption algorithm to the letter 5, and the letter 5 is an F. So what we have is we have M is taken to F. Okay, and we continue in this fashion. Yeah, well, we already know a 0 is taken to. Okay, 0 is taken to H. So we don't need to do that. What about 18? Where's 18 taken to? So when P is equal to 18, the ciphertext should be equal to 15 times 18 plus 7 modulo 26. Well, that means C must be equal to, let's just get our calculator again. It's 15 times 18 plus 7 gives us a value of 277 modulo 26. Okay, so when I divide 26 into 277, what's left over? Okay, well, 277 is equal to, it's equal to 26 times, divide that by 26, it goes in 10 times. Okay, so plus some remainder. What do I add on to 26 times 10 to give me 277? Well, clearly we add on 17. Okay, so what we have is 277 must be equal to 26 times 10 plus 17. Our remainder is 17. So what we have is our C value is equal to 17. Okay, so 18 represented the character S. So what we have is that S is taken to 17, and 17 represents the character R. Okay. And now that we've done 18, we move on and we do P is equal to 4. So when P is equal to 4, we get C, the ciphertext must be equal to A, which is 15, times the plain text, which is 4, plus B, which is 7, modulo 26. Once again, in this case, 4 15s is 60, plus 7 gives us 67, so C has to be equal to 67 modulo 26. So the question is, when we divide 26 into 67, what's left over? Well, how many times does 26 go into 67? It goes in approximately twice. So what we know is 67 must be equal to 26 times 2 plus some remainder. Okay, so, well, 67 minus 26 times 2 gives us a value of 15, so the remainder must be 15. So 67 is equal to 26 times 2 plus 15, and our remainder is 15. So what we have now is we have C is equal to 15, our ciphertext. Okay. So now, once again, we encoded the plain text P is 4, which was the letter E. So what we have is the letter E is taken to 15, and 15 represents the letter P. Okay. Continuing in this particular fashion, moving on to the next character, which is a 2, we end up with, when P is equal to 2, the ciphertext is equal to A, which is 15, times 2 plus 7 modulo 26. Okay. 15 times 2 is 30, plus 7 gives us 37, so C must be equal to 37 modulo 26. How many times does 26 go into 37? It goes in once. And what's left over? Okay, well, we have 11 left over. Okay, so actually, if I was to do it the way we're doing it here, what we now know is this, is that 37 is equal to 26 times 1 plus 11. Okay, so this is my remainder. Okay, this is the remainder here that we're interested in. So we have our ciphertext is equal to 11. The character P is equal to 2. Okay, when P was equal to 2, okay, the plain text 2 is a C. So what we end up with is that C is taken to 11, and 11 is the character L. Okay, nearly there. We have to do, I suppose, really 2 more, because we've already done 4. Okay, so we need to do 17 next. So when P is equal to 17, the ciphertext is equal to 15 times 17, okay, plus 7 modulo 26. Okay, well, 15 times 17 gives us a value of 255, plus 7 gives us a value of 264. So the ciphertext must be equal to 262 modulo 26. Okay. How many times does 26 go into 262? So divided by 26, it goes in approximately 10 times. Okay. So now what we know is that 262 must be equal to 26 times 10 plus a remainder. Okay. Well, 26 times 10 is 260. What do I add on to it to give me 262? I add on 2. So what we know is 262 is 26 times 10 plus 2. So my remainder is 2. So what we have is C is equal to 2. The ciphertext is equal to 2. From a character perspective, P was 17, our plain text was 17. Plain text 17 is OR. So what we have is OR must be taken to the ciphertext 2, which is C. So OR is taken to C. Okay. Oh, this was pretty long. I didn't think it was going to be this long. Okay. But our next character to do is the character 19. So when P is equal to 19, the ciphertext is equal to 15 times 19 plus 7 modulo 26. Okay. Well, 15 times 19 gives us 285, plus 7 gives us a value of 292. So we have C must be equal to 292 modulo 26. Okay. So once again, how many times does 26 go into 292? But more importantly, what's left over? Well, 292 divided by 26 goes in approximately 11 times. So what we know is 292 must be equal to 26 times 11 plus some remainder. Okay. Well, 26 times 11 is 286. So what we have here is that 292 minus 286 must be equal to OR. Okay. Well, 292 minus 286 gives us a value of 6. So we have 292 must be equal to 26 times 11 plus 6, okay, which gives us our remainder. So our ciphertext is equal to the remainder, which is 6. So in this situation here, we have the plain text character 19, okay, the plain text character 19, which was 19 was a T, okay, so T must be taken to the ciphertext character 6, and 6 is a G, okay. So we're just done now. So our secret, okay, is, well, it was I, wasn't it? It was, yeah, I am a secret. That's the plain text. This is the overall plain text, okay, and the ciphertext, okay, is, well, if we go back to our first run of this, okay, where we had 8, well, we have L is taken, sorry, I is taken to X, so this goes to X, okay. A, which was the 0, is taken to H, so this goes to H. We have 12, which was an M. M is taken to F, okay. A is taken to H. We have S. S is taken to R. We have E. Well, we have E is taken to P, okay. We have C. Well, we have C is taken to L, okay. We have R. Well, we have R is taken to C, okay. And we have E. Well, E is taken to P. And finally, our last calculation was in relation to the T, which was, if I can actually find this, oh, there we go. P is 19, which was a T, is taken to G. So our message that we would actually communicate would be, with no spaces, would be X, H, F, H, or P, L, C, P, G. And this is my secret code that we will transmit. Okay. Right, guys. I know there was a lot involved there. Okay, but the key to this particular algorithm is to choose. I suppose we know what our alphabet size is going to be. In our case, 26, and it's to choose two values A and B. The important thing is that both values A and B are less than or equal to M. Okay. And another condition is that the value of A must share no common divisors with M, and the characters or the parameters that we chose was M is 26, the size of our alphabet, A is 15, 15's divisors are 1, 3, 5 and 15, whereas 26's divisors are 1, 2, 4, 6, 12 and 26. The only common divisor is 1, that's good. And B could be anything at all, so B was equal to 7. And then we just substitute these in, along with our plain text representations, to give us our ciphertext. Okay, guys, I hope this was helpful. I know it was quite a long video, 28 minutes there walking through that. We would automate this particular process. You wouldn't be doing this by hand, but you can actually see we've encoded 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 characters we encoded here, yeah. And walking through and talking through this particular process took probably about 28 minutes. So guys, I hope this video was helpful, and once again, this is Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland. Okay, thank you.